So again, welcome to my presentation. I'm associate professor at Zayed University in Dubai, UAE. And today I will be presenting pedestrian attribute recognition using Gabor Wavelet layers. Okay, so this is the program for today's presentation. So I'll start with introduction, some related work, then I will briefly explain the proposed model and describe the results performed on some of the public data sets. Okay, so this is the motivation for the work. We have cameras now monitoring on many corners of our streets, malls, and outside on the streets and highways and airports and so on. So almost any major public space is now being monitored by authorities. So our problem of focus is recognizing pedestrian attributes such as age group and clothing accessories such as wearing a hat or a scarf, wearing a jacket, types of shoes, hair type, carrying anything, or even the clothing type, is it formal or casual, gender, the types of shirts worn, are the t-shirts or v-neck. Okay, so this is the focus of the work. So let's go to the next one. So there are tons of applications for this work. So we can gather statistics, all of these attributes that we will extract from the video, they can be used to gather statistics, and maybe then we can have targeted ads. This can also lead to group identification, image retrieval as well, and re-identification. So for example, if you have multiple cameras in a scene, you saw somebody with a particular attributes, you can do recognition in the second view using some of these attributes. So this is a challenging task. Why? Because first of all, the videos are very low resolution. The other thing is the appearance of pedestrian clothing. It's very diverse. One of the way you can see is this is describing a backpack. From the front view, there is no way to actually figure out, even for us humans, if the person is wearing a backpack or not. Also, messenger bag, I mean, that's one of the attribute being recognized. It's not really visible in the scene because it's very, I mean, from a particular view, we don't really see it much. Other things are illumination and camera viewing angles, such as this. For the messenger bag, that's really difficult to recognize. Color or illumination changes, things such as recognizing jeans, or with different lighting conditions, jeans might have different colors. They might be confused with leggings or some other kind of clothing. Also, there's a large intra-class variations, and the other thing is occlusion. Example of this is a backpack. Okay. So this is a very challenging problem, and the database are also very challenging. So this is the most traditional approach that has been followed. So the idea is to craft features or extract features and perform classification. And traditionally, this has been done using support vector machines. Okay. So in our work, we are using deep learning, where we're using the convolutional neural networks. Okay. So in some of the previous works, the way they did, in this example, for an input image, divided into a grid. So it's so you can see here, dividing it into 15 parts, and each part is around 32 by 32 pixels. Okay, and they train a convolutional neural network. You can see each part of the image passes through a separate network, and you have a final full connection layer, and then you have a classifier at the end using softfix layer. Okay. Another related work, again using its inception network and doing this front unit, back unit, and side unit, multiple units to train on the database. Okay. And also they are, in addition to attributes, they are also doing view predictor as well. So another work by authors Liu, Zhao, Tian. Okay. So they propose a novel multi-directional attention modules to train multi-level and multi-scale attention strengthened features. Okay. So you have two parts of the network. You have the convolutional layers using the inception modules, and then you have other attention feature nets, so using the attention network. Okay, and the features are fused at the end for classification. Okay, so for our work, we propose combining the Gabor wavelets. We call them as TGV, Trainable Gabor Wavelets, with CNNs for, so the acronym is PAR, Pedestrian Attribute Recognition Problem. Okay, so these trainable Gabor wavelets, they are basically the backbone of our network. Okay, and as we'll see in a minute, each of these wavelets, they accept a single channel input. So even if you have a colored image, we'll convert it into grayscale so that it will be a single channel input. Okay, the output will be multi-channel. Okay, and as you're using Gabor wavelets, we will look at the parameters. So the network learns these Gabor parameters. So it learns these the best filters suited for the data set. Okay, so the output from TGV and convolutional layers are stacked together. We call them as mixed layers, okay? And these are the really building blocks of our network. Okay, and we show that actually these are really effective and give us state-of-the-art results. So some of the pre-processing, which is kind of standard. So we do mean subtraction. So in other words, we from the training data set, we compute the mean image, and then we subtract it from all the other images from the database. And we also do normalization. So our image data is divided by the standard deviation obtained for each color space separately. So this is an overview of our Gabor wavelet part. So this is how we define the Gabor wavelet. These are the parameters. Okay. So we train the neural network to generate the hyperparameters for the Gabor wavelet. Okay, and also generate the Gabor filters. Okay. So we have an input n by n, and c is the number of channels. Okay. So we convert the input into single channel, and we perform the Gabor filtering, and the other part of the network is used to train or search for the best parameters for the Gabor filtering. Okay. And then at the end, we use the one-by-one filters to basically train the network in a way to, so I mean, if you're familiar with the Gabor filters, there is an angle that you can modify or that you can train. So that's what we do by this steering using one-by-one convolution. Okay. So the stability property of the Gabor wavelet. So this is the proposed architecture. For the input image, we divide it into three parts, three equal parts. And then we kind of pass each part through a separate layer. Okay. So this is, and we have 4 layers, or these are 3 branches, and each branch has 4 layers. We have the convolutional and the Gabor wavelet layer. Okay. And then we combine the features together, we concatenate this, and we have 4 such layers. Okay. So each mixed layer, 1, 2, 3, contains 256 channels from TGV layer and 256 channels from 3x3 convolutional layers, which we are calling 3-conv. For each 3-conv layer, we are using 3x3 kernel. Okay. And for all the convolution, we use the ReLU activation function, max pool layer of size 2 by 2, and best normalization layer. And you can see each branch connects to a fully connected layer. So two levels of fully connected layers can get related together for our final classification. So in terms of evaluation, we perform or test on one of the most widely used data sets. It's called the PETA dataset. So it consists of around 19,000 images, and the dataset has varied resolution. Some of the images are, let's say, from 17 by 39 pixels, while the remaining are large images. And this dataset actually contains images from various other datasets. Okay, so there's a town center dataset which contributes 37%, CUHK around 24%. Okay. So these are some of the attributes that this dataset contains. So it has 3 groups of age, and the 4th one is above 60. Backpack carrying other carrying lower, upper, formal, upper, former, lower, hat, jacket, jeans. So these are the attributes that we are kind of looking for in the data set. Okay, so we use Adam Optimizer with a learning rate, very low learning rate. We train for 50 epochs. There is also a dropout layer with the probability 0.5. We also use an L2 linearization, and the learning rate decays by a factor of 10 whenever validation accuracy remains unchanged for 15 epochs. So this is the results reported and compared with other methods. So we report accuracy, precision, recall, and F1 score. And as we can see, these are the other standard state-of-the-art methods, and our method reports greater or better accuracy and precision. And recall and F1 score are also quite comparable. Okay. So in this is just a sample where we're showing 3 images. So the picture on the left, it's rightly recognized to have age less than 30 and wearing leather shoes. Okay. So the center image is recognized to carry an object, and even though you can see there is quite a significant occlusion. So this is an example of false positive. Okay. Oh, sorry, this one. So even though there's occlusion, so I mean, of course the system cannot really recognize the kind of shoes and so on. So the right image is recognized to carrying a backpack, a formal upper clothes, which is not correct. Age of less than 30, which is also not correct in this case. So this is the class-wise accuracy. Some classes are recognized much better. This is mainly due to more examples for a particular attribute, and also some attributes are easier to recognize than the others. Okay, so the lowest accuracy is that of class upper body other. Okay. And the best accuracy is that of upper body thin stripes or upper body V-neck. If somebody's wearing a V-neck. Okay. So this is the results on this data set, and it's quite promising. So in conclusion, we proposed a multi-branch network to address problem of pedestrian attribute network and recognition. We used TGV, the Trainable Gabor Wavelets, to generate filters that best apply to the data set. And we show results on publicly available data set, and we show that we are very close, if not better than the state of the art. Okay. So that's work, and thank you very much for your attention.